The main topic of today that is our multiple measurements. So we're going to be talking about measuring things multiple times. So let's get started with that. So I wanted to start off today by giving you the actual objectives, which I don't usually do, but I feel like is good for us to understand and sort of center what it is that I want you to take away from this talk. So by the end of this class period, I want you to be able to understand how to store data when you've collected something twice, the idea that data sets can be reorganized, and you'll learn in lab how to reorganize them, the types of questions that you can ask with within subjects designs, and 2 ways to analyze within subjects data, and finally, how to interpret within subjects results. So those are our objectives today. So why am I talking about this? I'm talking about growth and change because within education science, and really most of social sciences, a lot of our questions are related to growth and change. We're often interested in questions about how much things are growing or changing over time. For example, how much do kids' reading skills grow during kindergarten? Or for my kinesiology folks, how much does your heart rate increase during exercise? Or does teacher satisfaction increase when we introduce some new curriculum? So if I have these things and I want to measure change, I have to measure them more than once. So I want to measure, if I want to ask how much do kids' reading skills grow during kindergarten, then I have to measure reading at the beginning of kindergarten and again at the end of kindergarten. If I want to know how much your heart rate increases, I have to measure heart rate before you exercise and again after you exercise. If I want to measure teacher satisfaction and how it increases when we introduce a new curriculum, then I have to measure teacher satisfaction before and after we introduce the new curriculum. So a variable or some construct that you measure twice is something that you expect to change within a person. So here I expect reading skills of one kid to change within that one kid before kindergarten and after kindergarten. And so because it's something I expect to change within a person, we call it a within subjects factor or a within subjects construct or variable. This word within subjects is very important to your understanding of how this all works. Okay. So within subjects repeated measures, I'm expecting that some of you may have seen this phrase before, maybe when you're reading papers. I don't think you did any within subjects repeated measures in GLM 1, if I've read your syllabus correctly. So this should be the first introduction to this concept. So you would use a repeated measures within subjects design when you have something that you expect to change within a person. And so you're going to repeatedly measure it. Vocabulary words. So we're going to use these designs or these types of statistical models when we want to tell if something has changed over time. And later on, we're going to want to predict that change. This is so bright. We're going to want to predict that change, but we're not going to do it just yet. Right now, we're just going to talk about whether change has occurred. Okay. So the first thing we're going to do is an activity. So let me show you what we're going to do next. I have if you go to the Carmen site, there is a link to an online like Google spreadsheet. And if you open that online Google spreadsheet, you'll see I have an activity for you. Oh, sorry, didn't mean to shut off my camera. Okay, so I have an activity for you. Yay, look, you're here. So what I'm asking you to do is to gather information about school districts and their social media engagement. So the research question that I'm working with here is, should these school districts be communicating via something like Twitter, via something like Facebook? Because I've got Twitter and Facebook here. So the type of information that I want us to gather is the district's most recent student enrollment numbers. You should be able to find a 2020 or 2021 using a Google search. Their estimated enrollment for 2018-2019. Use this website that I link right here. You can search for them. What you need to know here is that search for just a little piece of their name and the state of Ohio, and you should be able to find them. And then go and see if you can find their Twitter account by going to the Twitter website and the Facebook follower count, again, from their Facebook website. I'm going to put you in groups after you have jotted this information down. So I'm going to give you 10 minutes to find all of this information and just jot it down. I have mine on a little post-it right here. So just jot it down on a note. And then we'll come back together after 10 minutes and we'll do the second part of this activity. Any questions about the pieces of information that you're looking for? Okay, so you have looked through this spreadsheet, you've gathered your data. Was it hard to find that data? Meh? A little bit? Not so much? Seems like we had a little bit of disagreement, like looking through everybody's spreadsheets, they're basically aligned the same way, which is pretty cool and not the only option, but one of the ways to align it. So I talked to most people when I dropped into your rooms, I talked to you about, was this a difficult decision or was it pretty easy? A couple of you said you talked about it a little bit to decide exactly how to arrange it, but all of you ended up in about the same way. So I'm going to pull one up. Stop, don't do that. No. Sorry, I'm mad at Zoom. So here's one of the spreadsheets. I see many of you are here. We've got a couple of different districts. We ended up with about 8 or 9 different districts with different enrollments, and then information about 2021 enrollment, Twitter and Facebook followers. So I see a couple of things right here that I want to talk about in terms of just information. But let me come back to group 3 in just a second. So if you look at what group 4 decided to do, they decided to create 3 different enrollment variables rather than 2 different enrollment variables because they found 2018-19, 2019-20, and 2020-2021 school years. And it differed depending on which ones they were looking at. So if I take a mean of this across all of these districts, I would have a mean enrollment for 2019-2020. Whereas if we have some folks who did not distinguish between them, although it looks like everyone here has 2021 enrollment, 2019 enrollment. They all look a little bit different. But what I was trying to say is that if somebody ended up with 2018-19 enrollment in a 2019-20 enrollment, then that variable's meaning has changed. I can't stand this. Can't see any of you. Okay. So I want to go back here to something that we have here in group 3. So I see 2 things right now that will mess up your data information. And the first one is this tilde here
We
in
couldn't
the
find an exact
3600.
number, so
Yep, absolutely. So you couldn't find an exact number, but getting close is a good idea. With this, though, what would happen is that it won't read it. So if I say, like, sum these, oh, I guess it did read it. I don't know how. Well, if you read it into any sort of computer program that's doing statistics on it, it won't read it. So the keeping either leaving it blank or putting in the number as best you can is a good way to go. And the same thing with the asterisk, which is interesting. Is this for a different year maybe?
nope, I looked it up, and on the website, the IES website, that's the number it provides. If you just Google 2018 or 2019, 2020 data, it gives you a different number. And so I changed the number that the group had listed, and I wanted to provide the reason why.
Oh, smart.
In my
Interesting.
actual data set, I wouldn't include the asterisks. I would just include my number.
Mm-hmm. Good. And I want to say that I'm not trying to call you out for doing something wrong. I'm trying to point out as a good illustration and example of what strange things can happen and can mess up your data when you're not expecting it. Okay. So, we can get a lot of information here. I see a little bit so one thing that I think is really interesting sort of glancing at these, is there anything that stands out to you looking at this? How about what's a better way to get in touch with the people, for these people to get in touch with a social media? Should they use Facebook or should they use Twitter?
It seems to depend on the district.
It does seem to depend on the district, but that certainly is an analysis we could run to figure out whether it's people have more Twitter followers or more Facebook followers. How about, does enrollment change from 2019 to 2020? Can you tell that by eyeballing it?
I think overall they decreased.
Yeah, I don't know. Oh my gosh. Is that really true? It's a lot of kids. Interesting. Same here. A lot of kids. So this one is listed backwards temporally. So 2020, 2021 comes first, and then 2019, 2020. So interesting potentials, but none of it we can actually tell from just our eyeballs. All of it we'd have to test. Okay, thank you for coming with me on that journey. Let me talk to you about why on earth I just had you scour the internet for that information. Hopefully we can use this data here in a little bit to answer some of those questions. But first I want to talk about the kinds of variables we've just collected. So right here, we have two different measures of enrollment. This is a repeated measure, essentially. And so it's a within subject variable. Uh-oh. I've got some information here that Akron School's Twitter followers account number may be incorrect. It says, look at this. Oh my gosh, look at this, you guys. Facebook, 49. Twitter, 49. Our variables got confused in our copying and pasting. How about here? This one says it's Twitter is 49. And someone in the chat here says, actually, Akron has 7,000 Twitter followers, so I'm not sure where we got 49 at all. Is that Facebook or is it Twitter? You guys. Inadvertently, I get to make lots of points about data quality and how important it is. So can you see that with just that one number example, somewhere somebody's lines got crossed probably several people's lines got crossed. We don't know which parts of these data is actually accurate. So you now have a new homework assignment, which is to check these data, and you're responsible for your own sheet. If you're group 1, then on group 1, change some of the numbers to match what you think they are. Don't change anybody else's numbers, just the ones on your sheet. If you're in group 2, just change the ones on group 2's sheet. And at the end, maybe next time at the beginning of class, we'll take a look and see if they're the same now or if they're different. Oh, there's 2 Twitter accounts. Interesting. Still doesn't change the fact that some people think it's Twitter and some people think it's Facebook that has 49. So, interesting points. So the reason, why do I care about this so much? Let me tell you why I care about this so much. If we're trying to do something like calculate a mean of Twitter followers or try to correlate number of Twitter followers with, say, enrollment from 2019, and some of these people, it's a Facebook account, and for some of these people, it's a Twitter account, we don't actually have the right information. Our correlation does not represent the actual correlation between Twitter followers and 2019 enrollment. It represents nothing, something else entirely that's not related. They're not the same thing. And so our statistical conclusions are completely incorrect when we have incorrect data in the cells. So put that on your list of things to do. Check a couple of these out and see what you can find. And one of the first things we'll do at the beginning of class next time is double check these data. Oh my gosh, fun. Okay, now, the real reason I wanted to talk about this, other than getting to demonstrate all of those fun things about data management, is we have a within subjects factor, which is enrollment, which changes year to year. And we have a between subjects factor, which is Twitter and Facebook. So which one of these, what the actual, I guess it would be between subjects if you consider social media to be a factor. And social media has 2 units. The first one is Twitter and the second one is Facebook. So now, let's talk about why I care about that so much. So everyone chose to enter their data about the same way, but that's not the only way you could have entered the data. When we have within and between subjects factors, you all chose to enter them in a wide format, but could also be in a long format. So I'm going to talk about the differences between those two. So I have another example where I have a math assessment on kids and I've assessed them 3 times on math. I need a couple of things. I don't just need math assessment. I also need the child ID and I need the teacher's ID. And for fun, I'm going to have a between subject variable, which is household income. So I have just this thing that varies by family. And so there's 2 basic ways to structure this data that look like these. First, I have a long format where you'll see I have a lamp in my way, where you see I have child ID, teacher ID. So these are all the same teacher. These 3, oh, these are all the same kid. That's not correct. These 3 are one kid and these 3 are a different kid. You see that their ID changes? The income variable changes with the child ID. But then I have this variable, an index, which represents time. And then I have math in one variable. So you're going to repeat any between subjects information every time you measure math. But math is just one variable. And on the other side here, I have the wide format where you can see that it's 2 different kids. Each row is now a kid. They both have the same teacher. We have multiple variables for math. So I don't need an index anymore because it's implied by math 1, math 2, and math 3. So my between subject factors are only scored one time. Okay, long format, wide format. Why does it matter? Let me tell you about long and wide formats. The thing is that all of these analytic methods that you're learning in this class and in other classes, they've all been developed by different people who have different levels of familiarity with different types of data structures. And so some different analytic methods require the data to be structured in different ways. However, if you collect the data one way, you're not beholden to that forever. Data can be rearranged to fit the needs of an analysis, and you would do that in SPSS using something called restructure command. And so the restructure command, I think, it works better than many other programs. It works better than R, and it works better than SAS in terms of restructuring data, in my opinion. But it still is very confusing looking, so I'm going to show you what it looks like. Here is the restructured data wizard. And I don't know about you, but something about this, it just like brings up a whole bunch of anxiety for me to even see this form. So what do you want to do? Welcome to the wizard. What do you want to do? These are not helpful to my brain at all, in the slightest. So let's talk about, well, I'll talk you through what these are. So cases is SPSS's word for rows, and variables is SPSS's word for columns. So if you have a wide format data set and you want it to be a long format data set, you would need to turn some variables that you have, because it's wide, you have extra variables, you would need to turn them into cases. You need to turn them into rows. And the opposite is true if you have a long format data set but you want it to be wide. Then you would turn cases into variables. I think Susan's plan is to walk you through how to do this in lab tomorrow, so you'll have an opportunity to play with it. So I bring it up specifically because, you know, the way that data are structured and organized hasn't come up as much before now because we've just stuck with one row per person, multiple variables per person. But now that we have multiple time points measured in each person, there are two real schools of thought about how to organize the data. Now, repeated measures ANOVA is what we'll learn about today. The repeated measures ANOVA requires data to be, well, I say that next. Oh my gosh. It requires data to be structured in a specific way. So I'll describe that here in a second. So back to our primary question, which is how are we going to capture growth and measure growth within a data set? We can do that in the GLM with a repeated measures ANOVA. So I'm going to introduce the idea of this repeated measures ANOVA using the Sesame Street data set that we've used in this class before. It's an evaluation of Sesame Street, like how much they watch TV and how much they watch Sesame Street. And they're measuring kids twice. I believe it's the beginning and the end of the preschool year. And for this examination, I'm going to focus on numbers. So I have pre-num for time 1 number knowledge and post-num for time 2 number knowledge. So what's a research question that you would ask with repeated measures data? Well, the first research question that we'll ask is, did children's number knowledge grow from time 1 to time 2? That may not be the most interesting question, but it's a good place to start. In the repeated measures ANOVA, they're going to test this like this. They're going to say, is the difference between time 1 and time 2 equal to 0? The null hypothesis, null remember is 0, is that there is no difference between the two time points. So is the difference between time 1 and time 2 equal to 0? In other words, time 2 minus time 1 equal to 0. Is that the case? If we reject the null hypothesis, then we say that time 2 minus time 1 does not equal 0, and there's a significant difference between time 2 and time 1. If we fail to reject the null hypothesis, then time 2 minus time 1 is basically 0, or there is not significant change for time 1 to time 2. There's not a significant difference between time 1 and time 2. Do you see how we've reconceptualized change in the repeated measures ANOVA? We reconceptualize change as being how different is time 1 from time 2. Time 1 minus time 2 equals 0. Thanks. Okay. Now for repeated measures, SPSS, actually I think all of repeated measures math, requires that your data are oriented in a wide format. And just to remind you, this is what the wide format looks like in that example data set I showed you. Now we are in luck, my friends, because our Sesame Street data is already in wide format. You see I have an ID variable, I have pre-numbers, and I have post-numbers. To be in wide format, remember each measurement of a given construct must be represented by a separate variable, which is what we have, pre-number, post-number. Pre, post. So this person gained 4 numbers. This person gained 0 numbers. This person gained 31, right? Yeah, 31. So in order to do repeated measures ANOVA, I'm going to actually walk you through the SPSS text boxes, and I don't usually do this. I leave this to Susan most of the time, but I'm doing it now because I want to demonstrate that the way that the math works, you have to have specific factors involved. So I'm going to show you what those are by walking you through their point and click menus. Apparently I'm all about being mad at SPSS today because you're going to get this intimidating checkbox when you open this. So if you get this after you click on Analyze GLM Repeated Measures, you get some empty boxes. So what are these? I'm going to decode them for you. First, within subjects factor. What's a within subjects factor? Do we remember? You can type it in the chat. Something that changes within a person. A within subjects variable. Yeah, Sarah says change in time. Exactly. So our within subjects factor here is the thing that varies within people. So I've got time is going to vary within people. Number of levels. What does that thing mean? It just means how many times it was measured. So in our case, because we're doing repeated measures, and all that's changing is time from each time point. Time is our within subject factor name, and the number of levels is 2, because we just have a pre-test and a post-test. The heck is a measure name? A measure name is the thing we measured twice. So you could call it number, because that's what I'm looking for, is change in the number variable over time. So we can call it number, or we can call it num. And then once you've done that, here it is all filled out. You see I've got a factor called time. It has 2 levels. And then I have a factor called number. That's the name of the measure that's going to go be taken twice. So you'll notice that I haven't told it anything about the actual variables in my data set yet. I've just given everything placeholder names. And once you add, then you click define, and then you can actually start to put in the variable names. And I think it does this to try to make you, it thinks it's smarter than you, and it's just trying to make your life easier. So what happens now is that you get this little thing, which you've seen these boxes before, I think, in things that you've done, but it looks a little bit different because we have all of this sort of funky looking stuff over here. So what's this? Within subjects, we know that word. Within subjects variables for time. So 1 comma number means time 1 for the number variable, which I know is pre-number, pre-num. And 2 number is for the post test of the same thing. So this is post number. So you just find those variables and pop them over there. And now you can see why you're required. I said it has to be in wide format, because here you have to be able to put in one variable, the pretest variable here and the post-test variable here. So it's a requirement that your data be in that wide format. Okay, buckle in, guys. This output is wild. Here we go. All we've done here first is you get some information that your time 1 variable is pre-number, time 2 variable was post-number. Just like confirm, make sure that's good. That's fine. Here, these things are multivariate tests. So the multivariate test, the multivariate test goes through and checks that the mean differences are all 0. Is every difference 0? Now here we only have one difference because we only have time 1 to time 2 of one variable. If you have a much bigger model, then you have the opportunity to potentially see some more differences. But here we only have one difference, so there's, I'm actually surprised it even is able to run, honestly. This difference, it's just telling us, it's the same as the F test we'll get in a minute. It's telling us that these differences are not 0. Surprise. Okay, next you're going to get this little guy called the test of sphericity. Now the test of sphericity is testing whether the differences that you're calculating for your within subjects effects, whether those differences are the same across all of the groups that you may have. Now, we don't have any groups. It actually can't even estimate this because we don't have enough degrees of freedom for it. So, see, degrees of freedom, 0. So this one is moot at this point. But this does some things that I'll tell you about later. All right, so now let's keep going down this output. We end up with this tests of within subjects effects. Our measure here is number. That's reminding us what we're actually testing. Type 3 sums of squares. Those are just like you got in GLM and just like you got in regression, where you get a numerator and a denominator degrees of freedom and mean squared errors and an F test. It's all the same. So this, for some reason, it repeats it again for you. So you get a test of within subjects contrast. So you get the specific sum of squared errors for each component in your model. Here we only have one component. We just have time, which has 1 degree of freedom because there's only 2 levels for it. So this is just like the F test from your other GLMs, where you would say, we have significantly decreased the error in this model. This is a significant model. We can also get parameter estimates, just like you can for other GLMs. In this case, the parameter estimates is going to give you a test of whether each measurement occasion is equal to 0. So this is telling us that the pre-numbers is significantly different from 0, and the post number is significantly different from 0. Now we can get a more specific test of our question, which is, did math skills grow over time? Remember? We can get that by using this little guy called pairwise comparisons. The pairwise comparisons box will give you the difference between the two of the groups or across your factor. So here I have time 1 and I have time 2. This is time 1 minus time 2. The mean difference is -9, which is significantly different from 0. And then it also gives you time 2 minus time 1. Time 2 minus time 1, where the difference is exactly the same in the other direction. So this is telling me that from time 1 to time 2, kids are gaining on average about 9 points on this number scale. The other cool thing that this will give you is it will plot for you the estimated marginal means. Sarah, I will show you in just a minute. That's a really good question. So this is the other thing you can get is estimated marginal means. It'll just plot for you the difference between time 1 and time 2. You're getting the same information so many different ways. Look at this, 20 and 30. If you remember way back here, we had, oops, I went too far. 20 and 30, which are about 9 points apart, just like this is showing us. Okay, so within that, all signs are pointing to yes, there was some change from the first time point to the second time point. The F-test suggests that we have significantly reduced the error. The null hypothesis was rejected. The difference between the first and second time points was not 0. But like, honestly, that's not very interesting. I don't actually care that much that they grew. So the next thing we want to do is add some between subjects factors. So we're going to add gender to this equation. And in this data set, gender was coded as male and female. So this will give us a new question, which is change the same for males and females? So after following that same setup to get to what your factors should be, you'll notice that there's also a between subjects factor space. So we can put things here into the between subjects factor area. And then we have both within subject factors and between subject factors. First, we get some reminders about how everything is coded. Then you're going to get some descriptive information. Like right here, you can already start to see what's going on in terms of pre and post and male and female. So now our test of within subjects effects, remember you get one for each component of the model. And we're going to get a time variable and a time by gender interaction variable. You're going to use 1 degree of freedom here and 1 degree of freedom here. And here is your error. Again, you will end up with this overall F-test to tell you whether the model is significantly related. But like, haven't I always told you that you can't just put in an interaction into a model without the main effect? Yes, I have always told you that because, and it's here, it's just a between subjects effect. So it goes in the between subjects effects, whereas time by gender is a within subject effect because time is within person. So what I'm seeing here is that there's no main effect of gender. My F here is 0.02. It is not significantly different from 0. So the mean of boys and girls is the same. And I also see that gain is not significantly related or is not significantly different for boys and girls. That's what this interaction is telling me. Does the effect of time vary by gender? And the answer is no, it does not. We can take a look at them. There's this little guy called estimated marginal means. And it'll show you, look at this, it'll plot for you the difference between boys and girls here at time 1 and the difference between boys and girls here at time 2. You can see from this plot that it's basically exactly the same. Absolutely no changes. They're growing, and they're growing at about the same amount in this fitted model. Whew. Okay, so normally I would walk you through like 3 or 4 examples using a repeated measures ANOVA, but I have to tell you that other than these kind of cool graphs, I find the repeated measures ANOVA to be a little bit superfluous because there are so many other ways that you can fit the same data and get the same information in a much more generalized way. And as Sarah pointed out, she said, will the results generated be different than that of a paired samples t-test? And if I tell you no, then you also should be able to generalize that it will be basically no different than doing this in a GLM, in a regression model. So we can do all of this outside of this very hyper-specific framework, and we can work it within the realm of the larger space of GLM. So let's do that. Let's do that, but wait, before we do that, that's a whole lot of information that I just threw at you about this whole other system. Can I reiterate any points about this multiple time point repeated measures ANOVA concept?
I have a question, Professor.
Yeah.
So say you're looking at a question that has more than 2 time points, say 3 time points, pre, mid, post. Can you do that with a t-test, like a paired sample t-test? Or would you have to use a repeated measures ANOVA for that?
That's a good question. And the answer is it depends on your research question. So if you just want to see whether things are changing over time, then doing it with this repeated measures ANOVA is probably easier. Because with a paired samples t-test, you would need to test every pair on its own.
And doesn't that also increase one of the types of errors if you do paired sample instead of doing a repeated measures?
So yes and no. So yes, it does increase the type 1 error rate, I think. I can't remember off the top of my head which one it is. So it increases the probability of incorrectly detecting something that isn't actually there. Right? That's type 1. Yes. So if you, however, when you do this within repeated measures ANOVA, it still has the same problem. So it will automatically run all of those pairwise comparisons for you, and you will have to adjust for that error rate, family-wise error rate. So yes, you're correct. And that's when you would need to use the post hoc tests that you learned in GLM1. When you do multiple comparisons.
Gotcha, thank you.
Yeah. And I can show you how that works. I'll have to invent some data, but we can show you how that works. Okay, other things on repeated measures ANOVA. I know it's kind of not fair for me to introduce you this thing and then say, actually, I don't really like it. I just feel like it's so hyper specific that it is very useful if you have 3 time points in some instances, 3 or more time points in some instances. It can be very useful. Okay, let me show you a little bit about this next piece. So if you want to talk about change in a more general way, in the general linear model, we have a couple of options, but to be equivalent to the repeated measures design, we're going to use something called a gain score or a difference score. The difference score, it means just that. It's the difference between 2 measurement occasions. So you can also call it a simple difference score or a change score or a gain score. Sometimes you see delta y, change in y. To make a change score, you're going to subtract the performance at time 1 from performance at time 2. So delta y is just equal to time 2 minus time 1. That's it. Remember how I did that on the fly? We had one person who didn't change at all. We had one person who changed like 39 numbers. That's a change score. This change in y is an estimate of the amount of change that has occurred between your 2 time points. It's kind of nice because it has high face validity, meaning it's pretty intuitive what it represents. And it's often used as an outcome, not a predictor. When we want to predict how much change has occurred, this is our outcome that we can use. So, if we're interested in measuring how much change is really occurring, you need to make sure that you've measured the same thing twice. It has to be the same assessment, basically, representing the same conceptual domain. This is true in repeated measures as well. That both of the times that you've assessed something, you have to be measuring them on the same numeric scale. You want to have as minimal measurement error as possible. Nope, I am not talking about residualized change. This is also the same of the gain score. So think about this for a minute. If you have a change score, that's time 2 minus time 1. And if you have a change score that's very big, what does that mean? We have time 2 minus time 1 equals a big positive number. Yeah, it means time 2 is just a lot bigger than time 1. Sarah, it may translate into an effect size, but it's not necessarily, but probably. And if you have change that's close to 0, what would that represent? Exactly, almost equal. So you've got like that one kid that we saw who went from 39 to 39. They didn't change at all. Negative on the flip side there is, it was big and positive. Time 2 was bigger than time 1. Negative just means that time 1 was bigger than time 2. So it has, that's what I mean when I say it has high face validity. It's pretty easy to tell what it means. So how do you actually estimate this in the GLM? First, you need to calculate a difference score. So we have to make this new variable called number change, like how much change happened. And that's going to be post number minus pre number. Remember, y at time 2 minus y at time 1. So we're going to run that. And then we predict it. And I'll show you how that works right now. I'll switch over to SPSS for you. Okay. here is our syntax. So the first thing we can do here is get our new change variable. Okay, and from this change variable, let's get some descriptive information. So it looks like our minimum is -35, so that's somebody who had a very large change, but in the opposite direction as we would expect, all the way to 33, which is someone who had a very large change in the exact opposite direction. So what I can do, if my research question is, did boys change more than girls? Look at this. Number change, like change in number, by gender, will tell me if the amount of change is different for boys or for girls. If my research question is about whether change is dependent on the gender identity of these kids, then this is how I can test it. So here, you're used to these variables. You've got male and female. We've got descriptive information for each one. Here's that same between subject effects table that we've seen before. And here's our parameter estimates, where you can see that there is no significant difference between boys and girls on the amount of change that they make during the academic year of preschool. Now, for fun, I feel like we should compare them. What do you think? You all want to see the difference? For fun. I need gender in here. First of all, let me ask this. Does this part make sense about the difference between the change, the size of change by gender? Anybody have any questions about this part while I pull up the code for this one? Nothing? Maybe like, why not just do it this way? This is pretty easy. Okay. Let's compare the two then. Come here. Come here. Okay. Within sorry, all of my there we go. So here I have the code. Here I have pre-number 1 and 2. I have post number. Then I have my between subject effect of gender. I'm going to paste that down here so I can compare it. So when I run this, I have the same basic information, descriptive information at the top. And then I have my multivariate tests, which we talked about. The test of sphericity still can't be run because I still only have really just one difference to compare. Now I get this effect of time by gender interaction. Again, I'm seeing no significant difference here between time and gender. I mean, between genders by time. So I was gonna, maybe we could pull some. Look at our non-difference. They're gaining exactly the same amount between here and here. I've got our gain. So let's see, we go from 20 to 30 and it's -9. So let me come down here and see what we can find from our previous outputs. There's our parameter estimates. Look at that. There's our intercept of 9, which is the difference between pre and post test. And then for gender, our coefficient here about the difference in gain is negative 0.438. That may not map on exactly because of this is going to be represented as an interaction, but let's look. What did I say, 0.438? So not quite, because it's giving us a difference at time 1 and a difference at time 2, instead of giving us the overall. But I bet our test of sums of squared errors up here is also, again, this is representing it as an interaction, which is slightly less powerful than representing it as a main effect, which is what we're doing with this ANOVA method. Okay, so hold on. Hi. That was a lot of information I just threw all at you. What I want you to do now is sit with that, because we're not actually applying any of this other than some things you'll learn in lab tomorrow, but you're not applying any of this to homework this week. You'll apply some of it to homework the week after. So sit with this idea, and we'll talk a little bit more about 2 time point designs and 2 time point tests, and I'll pull up an example Adriana suggested of 3 time points. I'll pull up one of those as well to compare. And we'll talk about those next time. Take a look at your the online space. I'll put up a couple of more readings about this content for you to look through as well. Okay, thanks for coming. I'm sorry I went so long today. I really wanted to get some of that introduced to you, so I appreciate your sticking through it this late on a Monday evening.